All right, welcome to the Moons of Mars class, survey class. My name is Ken Ramsley. Jim Head and I will be moderating the class this week. We have a number of minor rules of the road here. One is that we collect questions and answers during the lectures, and we'll be going over those at the conclusion of both lectures. This week we have two speakers. We have Carly and Mihai, and Carly will be speaking about spectroscopy, and we'll be talking about dust. And Okay. So anyhow, without any further ado, please feel free to put in comments and questions into the box, and we will collect those and discuss them at the end. Okay, Carly.
Okay. Hello, everyone. Okay. I'll be talking about space weathering on Phobos and Deimos, and we have a lot to go through, as Ken mentioned. It's really a wonderful double header that we have with space weathering that I'm going to talk about and some of the dust that Mihai is going to talk about. Let's see, it's not moving. Let's see. Do I have to hit something down here?
Just do your first click on the arrow, then the keyboard after that.
Okay.
Yeah.
Okay, let's see if that works. First arrow.
Yeah. Okay.
Okay.
Okay. Well, these are the various topics I'm going to touch on today. First, why we suspect space weathering might occur on Phobos and Deimos. And in order to get into that topic, we do have to talk about some of the things we've learned both for lunar space weathering as well as asteroidal space weathering. And from there, we'll branch into what we know or don't know about the character of Phobos and Deimos itself. And at the end, I'll give some summary and a few conjectures. You may remember from Andy Rifkin's discussion on the color of Phobos, the spectrum shown here, which is from the visible to the near infrared for both Phobos and Deimos as well, really doesn't have any major absorption bands that are highly diagnostic of pyroxenes and olivines, etc. It's sort of a featureless spectrum, but on Phobos, at least, there are two different forms of this, so to speak. There's a steeply sloped, quote, red unit, and there's something that's a flatter, or what's often called the blue unit. And these are spatially coherent across the surface of Phobos. But both of these kinds of terrains are essentially featureless in terms of the diagnostic absorptions that we know and love for many of the other bodies in the solar system. Well, let's compare them to other bodies of the solar system. Down in the lower right is these spectra, and again, all these little squiggly lines are at the same scale. Phobos and Deimos is shown in the lower left. They're all scaled at a wavelength in the visible, but you can see, again, the character of Phobos and Deimos are this sort of featureless spectrum that's relatively steeply sloped, and then one part of Phobos is flatter, or that's the bluer unit. If you look at the variety of asteroids or other small bodies in the solar system, there are several that have wonderful absorption bands, and we'll talk about these, the S type of asteroids. In the red are where near-Earth asteroids occur, and we are going to look at Eros, and we're going to look at Itokawa, which has beautiful, well-defined absorption bands. The Bennu, the OSIRIS-REx, is something quite different. We don't have samples from that yet, so you'll have to wait a few years before you can understand them. But the main belt asteroid Ceres and Vesta we will talk about. In particular, Vesta has beautiful, strong absorption bands. However, you notice there are asteroids that look very similar to the overall spectra of Phobos and Deimos. I show one on the left there, the D-type asteroids, which again is a featureless spectrum, has this red slope. For all the world is very comparable to what we see on Phobos and Deimos, as is highly space-weathered or soils, well-developed soils on the moon. Which is what's shown in the upper right. So here we have a conundrum. Which does Phobos and Deimos represent? A asteroidal kind of composition, clearly not some of these S-type asteroids, but there are some asteroids that have spectra that are very similar, or is it a very well-developed, highly weathered material such as typical of lunar soils? Well, that's what the nature of our discussion today is going to be about, and need to comment a little about what space weathering is. It's really an array of processes. There's not one that you put a material out and boom, it becomes space weathered, but there's many processes that are occurring simultaneously to alter the overall characteristics of the surface by some measurable property, whether it's a spectrum, albedo, what have you. It's an alteration that occurs when a material is in the space environment. Now, I want to emphasize, and this will be a theme you'll hear over and over through this discussion, there are many processes involved and there are many products. So it's not one process, it's not one product, but there's many that are interwoven depending on where you are in the solar system. Here's a figure that summarizes that. The original was developed by little technical difficulty here, by Sarah Noble about a decade ago. We've learned a lot even in the last 15 years, and this figure has been added to with what we've learned, and what I'm showing you here is what on my computer is already version 4, but it highlights the fact that there's many processes associated with the solar wind environment, micrometeorites, larger meteorite environments, shock mixing, breaking up, putting back together. A lot of these processes are all occurring simultaneously on any airless body. Now, for lunar-like space weathering, and I'll go through this briefly, I'll give you a summary of it. The principal processes involve micrometeorite bombardment, which includes a little bit of vaporization and deposition of the products, as well as solar wind sputtering. Either of these processes can produce what's called nanophase metallic iron, coating the individual grains of the regolith, and we'll look at that as one of the classic forms of space weathering that we understand now from the lunar environment. When we look at Vesta, it's a completely different environment, completely different products, completely different processes, our involvement. And in particular at Vesta, the primary processes involve contamination by exogenic materials, just a little bit, but enough to make a major effect, and then mixing with the regolith. And we'll look at that to get you familiar with that process and product as well. So the question of the day is, which of all these processes that we're going to walk through are actually most active on Phobos and Deimos? Can we tell, or do we have a concept, an idea of which of these are in fact most prevalent on Phobos and Deimos? Well, let's start with the moon. What we understand about the lunar processes, and this will be condensing several decades of work into just a few slides. First of all, what you see here is on the left is a nice lunar basalt, a lunar basalt powder shown in blue, which has these beautiful, highly diagnostic absorptions due largely to pyroxene, but mixed with plagioclase and other components as well. So it's a beautiful basalt, but what you see just below it in sort of the brownish line is what a lunar soil looks like from the same site. So somehow you have to take a nice rock when it's broken up and do something to it such that the soil has the characteristics that you see there. And that's the classic trend that we see in lunar space weathering. We see it when we look remotely, and that's what's shown on the right. When you look at a very fresh crater that's exposed, has been recently excavated, and you see again the highly diagnostic properties of fresh material, the pyroxenes in this particular crater, which is in a basaltic area. But as you go from this fresh crater to surrounding soils, you get the same sequence that we see in the lunar samples. Namely, the surrounding soils have this more degraded, this weathered character to it, which is just the same thing that we see in the lunar samples. And with time, then, in both the samples and with the remote measurements, you can see that the soils in the visible part of the spectrum become darker. And these diagnostic absorption bands become much weaker. But also you can see, although it helps if you scale the data, such as this. If you take the the remote data and scale it at a given wavelength, you can see that the overall spectrum of the soils have this steep red-sloped continuum. And this is characteristics of lunar type of space weathering. This is an important part to remember, because this is going to be a theme when we come and look at other things that is not always the case for other bodies. When we first recognized this, when the samples were returned, the thought at that time, so if you go back to the older literature, you'll see a discussion of, well, it's the agglutinates which is causing this effect, and therefore the agglutinates is the answer for space weathering. And since agglutinates are unlikely to form on small bodies with low gravity, space weathering might have no effect on small bodies. That we now know is incorrect. So if you read those papers, please read them with a grain of salt and read the remaining literature over the next several decades. Our current understanding is that the agglutinates are not the cause, they're the effect of space weathering. They're one of the products that are produced in the lunar environment. But the key component that creates the optical properties is these nanophase opaque forms of iron on soil grains. And I need to explain that to you and show it to you in a little more detail. This was recognized now almost 20 years ago when instrumentation became available and you could look at the details of lunar soils in the laboratory. And what's shown here is now a nanoscale of a section across the grain. The one on the left is a plagioclase grain, and for those of you who are petrologists, you know plagioclase doesn't have a lot of iron in it, but the rims of the plagioclase iron is peppered with these nanophase metallic iron components, which do not occur in the interior of the grain. There's a scale there, so you can see that these are really tiny, a few nanometers in scale. Shown on the right is an agglutinate grain, these heavily processed grains on the surface. And you see, again, these nanophase irons at the surface. In fact, you see, in this case, a layering of these nanophase irons. On the interior of the grain, you see these grains have grown to be much larger, and the character of them on the interior of the grain, which are recycled multiple times, the metallic iron component are much larger than these nanoscale which occurs on the surface. Once that recognition became common and well known, several experiments were done, and what was recognized after a long series of investigations was that the optical properties that we can observe on both lunar samples and remotely are tightly coupled to the character of this nanophase iron. Nanophase iron can be measured by a process called the Ferromagnetic Resonance. It measures a single domain iron. And this was known early on. It's strongly correlated with the amount of this nanophase or single domain iron. What was less commonly known, but which became obvious as experiments with samples became more highly focused, is that the characteristics or the properties of this nanophase iron are directly related and can be measured spectroscopically. And the more of these nanophase iron components that you have, the effect is directly linked to the properties of the nanophase iron. This is shown more closely here with some experiments that Sarah Noble did to create nanophase iron of a particular size and then to include different abundances of this nanophase iron in a transparent matrix. And what you see is essentially reflected in what we see in the samples, namely that those materials that have just small amounts of this nanophase iron have a certain characteristic, and the more of this nanophase iron that is included in the process, which essentially is accumulated on the surface of grains, is a much more distinctive signature that is seen in the experiments such as the high iron or the very strongly iron-bearing lunar soils here. So this link between the characteristics of nanophase iron and the direct measurement and observation in the sample help resolve what's causing the particular space weathering in the lunar situation. So this is a condensation of several decades of work, multiple papers, that has come to allow us to have the recognition that in the lunar particular situation, the production of this nanophase iron on the surface of grains, either by the micrometeorite vaporization process or by solar wind sputtering, either way, what's involved is the mobilization of specific iron atoms that then accumulate on the surface of grains in the single domain iron form. And the longer you do this, and the more iron you have in the surface, the more it accumulates, and you can see the progression of space weathering on the lunar samples and materials. Well, is this same process likely on asteroids? Well, one of the most abundant kinds of asteroids shown here is the distribution of asteroids in the solar system as a function of distance from the sun and inclination. One of the most common types of asteroid is what we call the S-type asteroids, shown, for example, on the right part of your screen. And the thought was, well, the most abundant type of asteroid should surely correlate then with the most abundant type of meteorite, namely the ordinary chondrites. Well, that ensued a major debate that raged for years about, are these S-type asteroids and ordinary chondrites related? Well, here you see spectra of a classic S-type asteroid, Eros, and some ordinary chondrites, and they're different. They're different in that the asteroid has the steeper continuum, it has weaker bands. So one group of people thought, well, this is just like lunar. It's just not as much, just a little bit of space weathering. And another group says, no, it can't occur because of the environment on asteroids. This has to be a compositional difference. These asteroids have a lot more iron in them, and they're nothing like the ordinary chondrites. Well, as you probably know, their near spacecraft went to Eros. It orbited Eros, and it landed on Eros and was able to put some of its compositional instruments in the dirt on Eros. And in a series of papers, it was shown quite clearly from the elemental measurements that were directly made on this asteroid that this asteroid does have the composition of an ordinary chondrite. A little bit later, the mission to Itokawa, the Hayabusa mission, again spent many years at, or not many years, many months at Itokawa. Shown on the right is telescopic measurements of this asteroid, which again, when compared to an ordinary chondrite, has this steeper continuum and slightly weaker bands. But Itokawa, or Hayabusa, brought back a few samples from Itokawa, which once they were measured in the laboratory, absolutely showed that this particular asteroid is an ordinary chondrite-like parent body. Not only that, it's an LL ordinary chondrite. There's no question about the particular kind of composition. Now, relative to our discussion, not only is this S-type asteroid a LL chondrite, but because we have samples and can look at the grains the same way the lunar grains were looked at, you can see in the sulfur and iron content that, again, as we saw on the lunar samples, we see this nanophase layer of iron particles, in addition to sulfur particles, which was an interesting addition to our understanding. Okay, so where we are for the moon and the near-Earth asteroids, prior to Dawn's arrival, we know the optical alteration is largely dominated by the accumulation of nanophase opaques, whether it's nanophase metallic iron or other opaques such as iron sulfide that occurs in the asteroidal environment. And both the solar wind and micrometeorites are important in this process. The near-Earth asteroids that were visited, however, had less processing than we found on the moon, which was a very important aspect of understanding the overall character. Okay, well, what about a main belt asteroids? Those others that we looked at were near-Earth asteroids. They were S asteroids. What about main belt asteroids? And in particular, what about Vesta? Well, here's a spectrum of Vesta in blue obtained before Dawn arrived, compared to a class of meteorites called the Howardites, Eucrites, and Diogenites. And they're perfectly happy to have these meteorites provide an analog for the surface of Vesta. And in that case, space weathering is not really needed. Recall that in the lunar case, we had this major difference between a rock powder and a soil. They're completely different. Whereas what we see here on Vesta is it's the rocks, the HEDs, and Vesta itself have the same characteristics, and we don't need any of the lunar-like space weathering. However, whoops, got to get the buttons right. When Dawn got to Vesta, what we found was, oh, wait, there is space weathering. Here's a lovely fresh crater with rays right next to a slightly older crater where the rays are completely disappeared. There's other examples across the surface where clearly some process is removing these fresh deposits around some of these most freshest craters. Some form of space weathering does exist on Vesta. Well, next thing you want to do is look at the spectra, of course. Here are some spectra obtained for this area. The red spectrum is a background area of an unweathered area, whereas these nice ray-like materials are brighter, and they do have a slightly weaker absorption. But when you scale all these spectra, shown on the right, you notice they all have the same overall continuum slope and do not follow the same way that we were looking at when we were looking at the lunar case, which had this steep overall continuum, and which we recognize is linked to this development of nanophase iron. So what this tells us is that on Vesta, there are prominent variations in band strength and albedo, but no related variations in the near-infrared continuum, which implies that at Vesta, there's none of these nanophase opaques developed on the surface of grains in the regolith. Whew. Well, okay, then that leaves us with two big questions. What is causing this space weathering on Vesta, and why hasn't the nanophase iron developed? Well, to answer the first question, it really is a matter of scale of opaque particles. You notice the bright areas on Vesta became darker. There's ways to do that other than forming nanophase iron on the surface. And what's shown here on the left is a meteorite, a eucrite in particular, where there's two different types of zones within the same meteorite, one of which is darker than the other. If you scale these two spectra, the orange and the blue one, as we see at the top there, scale them in the visible, essentially what you see is weaker bands in the darker ones, but no continuum slope. And the way you can do that, which is quite different from what we were discussing on the lunar case, is by having opaque components. You need that to make it darker, you need that to make the bands become weaker, but they're larger particles. They're 3 orders of magnitude larger than the nanophase iron. They're micron size, which is tiny. If you put it under a microscope, it will pepper it, it will be submicroscopic. But this difference for the size of the particles in the one case with the meteorite simply causes darkening, but a neutral color, whereas when you have the nanophase particles, it gives you this overall red continuum slope. And this was again shown in the experiments that I alluded to earlier. So we have a way of darkening Vesta with a spectrally neutral absorbing material that has to be well mixed in the regolith. Well, what kind of material can do that? Well, fortunately, we do have a explanation for that, namely that small class of carbonaceous chondrites are found in many of these HED meteorites. And furthermore, some of the results of the Dong experiment has shown that there's regions of hydrated material which is coordinated with the distribution of low albedo material, again consistent with contamination by carbonaceous chondrites. So there's a perfectly self-consistent story for what's causing the alteration on Vesta, namely it's a minor mixing with small amounts of contamination because of where it is in the asteroid belt. Why has nanophase not developed on Vesta? Well, this is a longer discussion. We have many reasons for this. I've listed them here in order of likely importance, but I'm not going to go over them in any great detail. One that we know is not the case is that it's not true that Vesta's surface is young. It's still old. Okay, so key lessons that we've gone through, and now we're going to get to Phobos, is that there are various processes throughout the solar system that are dominant at different times in different places. And it's very important that you have the location identified and the processes at least understood to the extent that you can. Okay, here's a summary that I just walked through, but I want to get to Phobos. Okay, what about Phobos? Phobos we know is old. Even Stickney, the crater, is old, and therefore the surface is old. The regolith is old. Coming back to our overview of Phobos and Deimos compared to other bodies in the solar system, well, maybe it is space weathered, similar to the way we see on the moon, this really heavy development of nanophase iron. Or maybe it's it's a particular kind of asteroid that's not one of the ones we've looked at. The ones we've looked at, we can understand the character of those regoliths, but maybe it's one of the asteroids that we haven't looked at. We do know that the properties of Phobos and Deimos are regular. In addition to the telescopic data, Andy went through the more recent data from the spacecraft that are at Mars, and again we see the relatively featureless spectra that dominate the overall character. However, there is very strong variability across Phobos when you get to the higher resolution, and we have two of these images from HiRISE. I wish we had more, but there are variations. We see small little fresh craters in the surface, but not all fresh craters have the same characteristics. Some are bright and red, some are bright and blue. There are boulders on the surface, but we don't have spectra of the boulders. Wish we did. Our understanding of Mars' two moons is very, very data limited, both in spectral character, coverage, spatial and spectral resolution. However, we do know that Phobos and Deimos appears to share the same regolith. Phobos and Deimos basically look alike. So somehow this is linked to their origin and their evolution where they are. And this was discussed extensively in some of the previous presentations. Are they captured asteroids? Are they accreted from a major impact into Mars? If they are captured asteroids, they must be of the same type, this unusual D type that we haven't seen, but you have to have that for both asteroids. If it's hard to do it for one, it's going to be hard to do it for twice. And as you've heard in previous discussion, this is unlikely, not impossible, but it is unlikely. If they accreted from a major Mars impact, it might be a little easier to make them the same. Clearly, as you heard from Robin and Joe Burns, both probably started from highly processed material, and their space weathering environment is similar, namely they're in the Mars environment. We don't have an answer for the space weathering on Phobos or Deimos, so I'm instead going to make a story up that is at least consistent with the data, but we don't have enough data to show this. And let's say we'll take the impact environment because that seems to be the more likely based on what we know. After the Borealis impact event, Phobos and Deimos accreted from from an anhydrous material, whether it was from Mars mantle, from the impactor, whatever. It had to have had some mafic or iron-bearing component in it. Clearly minor heterogeneity was maintained, but neither evolved beyond a coherent rubble pile. This was something that Sasha Basilewski pointed out. A regolith was developed and mixed with dust in the Mars environment. You're going to hear a lot more in the next few minutes from Mihai. And this next to the last bullet is probably the one that is the most problematic. We have the least information for. Clearly the regolith probably has been recycled many times on Phobos and Deimos, but has it formed these nanophase iron coatings or not? And this is something we don't know. If it's not a captured asteroid, the implication is that it probably has, but we don't know how it's done that. And then, of course, the dynamic height and the configuration of Phobos in particular will redistribute the material across the body for the patterns we observed. So that's as far as I can leave it. And we'll go to the dust discussion from here.
Okay, great. Thank you very much, Carly. Yeah, we'll move straight on to the next talk. Our next speaker is Dr. Mihai Horanyi. Dr. Horanyi received his PhD in space physics from Loránd Eötvös University in Budapest. Dr. Horanyi had joined the Laboratory for Atmospheric and Space Physics in 1992 and the Department of Physics at the University of Colorado in 1999. His research interests focus on the theoretical and experimental investigations of space and laboratory complex dust plasmas, including electrodynamic processes and their role in the origin and the evolution of the solar system, comets, planetary rings, plasma and plasma surface interactions. His research involves dust charging in situ and remote observations of dust, dusty plasma laboratory experiments, and space hardware development. Mihai?
Thank you.
Mihai, we don't see your camera right now. Could you go ahead and start your webcam?
Okay. You see me?
No, we don't see your camera just yet. Now we see you.
Yep.
Do you see my slides?
And we see your slides fine.
All right, then I would like to get going. I have a small outline that I would like to go through today. Dust impacts on airless bodies. And the best example I have is the lunar dust environment. I have certainly much more knowledge and data about the moon than Phobos and Deimos, but I will nevertheless tell you the expectations. Finally, I would like to tell that in addition to dust impacts, solar wind exposure can also do interesting things. So this is the first slide from NASA, which just reminds you about Phobos and Deimos. I don't want to, I think when the slides will be available, please look at the comparison between these two objects. The next slide says shooting stars versus impact ejector clouds. So comets and asteroid collisions generate a lot of interplanetary dust in the solar system. And you are familiar with shooting stars because the Earth has a thick atmosphere and most of the material, the small dust particles, burn up and you could see them. As opposed to, if you were to think of Phobos and Deimos, certainly the moon, these particles hit the surface and there is nothing directly because there is nothing to slow them down, and they make small little explosions, and when in addition to neutrons and plasma they generate secondary dust particles quite a bit. And we do have models for ejector clouds, and believe it or not, our best example before we had the LODI mission to the moon was Galileo measurement at Jupiter. The icy moons of Jupiter were noticed when the Galileo dust detector flew by. The impact rates went quite high, and we do have models how to describe ejector clouds depending on the size of the object. Small objects like Amalta and TB at Jupiter, I will show you in a second, probably Phobos and Deimos at Mars, have a hard time hanging on to the ejector clouds because their escape speed from these objects is quite small. As opposed to the Galilean moons and our own moon, the escape speed is much higher, so most of the dust will remain bound. And the plot on the right shows you, for example, for a 100-kilometer object, the dashed line is the bound and the dotted line is the unbound, and the continuous line is the total of the expected dust density as a function of height. The model is quite elementary in a sense that we simply assume that the mass production rate from the surface has to do on the left side with F, the flux of incoming particles, the yield, which is typically a few hundred to 1,000, the mass ratio of the incoming versus the produced amount of dust and the surface area of the object. And because we have no better understanding, we assume that everything is a parallel distribution, for example, the cumulative mass distribution and then the speed distribution of the ejector particles are a simple parallel. Actually, we do have some lab results to support these ideas, and surprisingly, the mass and speed distributions to a good approximations are decoupled. They are independent from each other. So this is what we knew at Jupiter, and these are actually the edge image of the Gossamer ring. You see Amalthea and Tb, those little white crosses are the extremes of the orbit, and what you see is the dust being produced due to interplanetary dust bombardment, and the particles that are generated from these objects simply inherit the eccentricity and the inclination of their source bodies. And you should certainly expect things at Phobos and Deimos, and certainly on the moon. And for the case of the moon, we just recently completed LADI, the Lunar Atmosphere and Dust Environment. This is the picture of the moon, this orbits of LADI, which stayed there for about 6 months and made ultraviolet observations and neutron mass spectrometer observations, and also it carried a dust detector to look for these ejector clouds. This is the orbit of the spacecraft. It arrived at a 250-kilometer orbit. After months or so, when all the instruments were checked out, it dropped to an orbit somewhere between 30 and 100 kilometers, and it stays there till early April of 2000 or mid-April of 2014. This is the instrument. This is an impact ionization dust detector. Dust. Can you see my arrow? Hello?
Yeah, we're still here.
Okay, so dust particles moves from left to right, hits our hemispherical target, makes a small puff of plasma electrons and ions, and the electric field set up this instrument makes the electrons recollected on the target, and the ions are into an ion detector, which has a much larger amplification. The signals look like this on the right. The top two are the ion signal and the electron signal that we collected at the dust accelerator, and the bottom two is once we were in orbit, and by comparing the rise times and the shapes, we can tell you how big and fast a dust particle hit our detector. The results are shown in this slide, which is time versus the daily average impact rate. We managed to have about a hit a minute for particles at least as big as 0.3 micron in radius, and maybe 1 every 10 minutes of particles that were bigger than 7 micron in radius. And then you notice these various periods that are marked with blue lines. Those are special because those are the periods when the moon was exposed to meteor showers. The meteor showers that we on Earth enjoyed as shooting stars, on the moon they just made the density of the cloud around the moon higher. This is the average density as a function of height in units of 10 to the minus 3 per cubic meter. The color code is the radius of the grain, and the back continuous line, which doesn't fit the data above 40 kilometers or so, is our expectations based on the models we developed for the icy moons of Jupiter. So clearly what it tells you that the speed distributions are very different. Most of the particles that we are detecting are their turning points, so the height that we are detecting them is intimately related to their initial speed, which I will tell you or show you in a second. Most of the particles are tiny, and the cloud extends well above 100 kilometers over the lunar surface. This is the cumulative mass as a function of height. The total amount of dust that is in flight above the lunar surface is about 120 kilograms at all times. which is, by the way, a tiny fraction of the tiny lunar ionosphere or atmosphere. So the dust contribution to the total mass budget above the lunar surface is less than a percentile, but it's there. The last slide is what we derived as speed distribution, which up to 400 meters per sec follows the expected power law, but it certainly turns over and starts dropping much faster than what we have observed at an icy surface, the Galilean moons. Maybe because the regolith is a very different material, how it responds to high-speed impactors than the icy moons do. This is the cloud. You notice that it is very asymmetric. The black parts are the parts where we could not make measurements or we didn't spend any time. And the color code is the density. And notice that in this plot, the sun stays on the left. The moon around the Earth is moving in general in the orbital motion of the Earth's moon system is in the up direction. And certainly we see a much higher density in the ram direction than anywhere else. And that was a surprise because around the Galilean moons, the clouds that we noticed seem to be spherically symmetric, not at the moon. In fact, I could show you the density as a function of local time. Noon is the subsolar point, midnight is 0, and the direction of the orbital motion is 6 o'clock. And notice that the dust density peaks are actually not directly in the ram direction, but slightly canted towards the sun, 7 or 8 o'clock local time. We try to figure out what is happening, and we used a NASA model, the expected impacts to the lunar surface. And of course, we are not measuring the impacts, we are measuring the product of the impacts, the ejecta. And from lab measurements, we had some idea how the incoming flux is related to the amount of dust that you are producing as ejecta. It is a weak function of the mass and it's a strong function of the speed. So this is what NASA would predict. Notice that certainly there is a strong ram, anti-ram asymmetry that is somehow matching what we were measuring. More importantly, of course, we could try to open up what goes into the NASA models, and the directionality that you are seeing indicated with this arrow does not belong to any of the sources. The major sources that we know from radar, ground-based radar observations, are what we call helion, that's appear to come from the sun, apex, that seems to be coming from the direction of the motion, and the anti-helion sources. And then one can build a model is to take a linear combination of these three, the blue, the green, and the red, the helion, anti-helion, and the ram direction, and make a fit to our data. And it does work out remarkably well that the linear combination of these three sources, which is the red, the green, and the blue, if you add them up, you get the continuous red line, and the gray dot represent our measurements. So we really see the same kind of sources of meteorites as ground-based radar people do in our ejector clouds around the moon. Of course, we do see the meteor showers. Certainly they come with big enhancements. We saw at least 5 of them. 4 of those were readily available in ground-based the catalogs based on ground-based observations. It seems that we found one that is an orphan, at least for now, because there was no corresponding radar or optical measurement that would indicate that there was a stream when we have seen the one in late March. So, just like the moon, Phobos and Deimos are also exposed to interplanetary dust particles. They have a regolith, so I expect there is an ejector cloud around them, and we could certainly build a model. And this is what I expect for the lifetime of particles ejected from Deimos as a function of their radius in microns. And depending on their size, if they are really tiny, the solar wind induced electromagnetic effects would really limit their lifetimes to be very short. In less than a day, they're going to be picked up and carried away by the solar wind. Somewhat bigger particles are vulnerable to radiation pressure perturbations. Radiation pressure is conservative force, so they keep their semi-major axis, but they lose angular momentum and they be driven to hit Mars or get absorbed in the atmosphere. And then the largest particles, depending again on the size, they will recollide with actually either Phobos or Deimos and get lost from the system. So by simply following a lot of particles, this is what I expect that the dust tori would look like at Mars. The green dots are the Phobos torus and the red dots are the Deimos torus, and they are spread because these moons have an inclination with respect to the ecliptic plane, and radiation pressure force is forcing them to leave that plane. That perturbation, the further you are from Mars, is more important. So the Deimos torus is going to be spread in a big volume, and the Phobos torus will stay reasonably flat. That is, of course, a prediction. I do not have any direct observation. There was a hint long time ago in the Phobos event 1989. This is a Russian spacecraft, Phobos 2, is flying and couldn't actually quite complete the mission, but when the first time it flew through the orbit of Phobos, during the closest approach, this is the closest approach to the orbit of Phobos, there is a little hiccup, little drop in the magnetometer data, which people interpreted that, that could be a signature of the torus, of the dust torus that is generated from Phobos. You could certainly look for these things, and there were certainly Hubble Space Telescope efforts to find the dust torus around Mars, and these horizontal lines show our ability to look for these dust as far as their optical depth goes. The search went down to 10 to the minus 7, 10 to the minus 7.5, and the expected optical depth is much below that, certainly for Phobos, and we are at least an order of magnitude away from Deimos. So our best chance eventually is to do in situ measurements, just like we did that around the moon. If you could fly around or at least have close flybys from Phobos and Deimos, or near Phobos and Deimos, you have a chance to find these clouds. This is the prediction for the Phobos density as a function of height, altitude versus density in units of particle number per cubic meters. So if you were to be able to look back towards the sun and see small particles in forward scattered light, that might also be useful, because at least close to Phobos, the optical depths would be 10 to the minus 6, 10 to the minus 7. Should you have a spacecraft that could go in eclipse and look back towards the sun, you might find the cloud. One reason you might be interested, because the dust that is generated from Deimos, a small fraction actually will end up on Phobos, and it will arrive in a non-uniform way. It will catch up. It's when you drop you develop an eccentricity that you are faster, so you're going to catch up on the trailing side and deliver most of the Deimos dust to the trailing side of Phobos. And that's about 2 to the 5 kilogram of mass per year. So maybe there is a reason that spectroscopically these two objects are similar, because certainly Deimos seems to be able to contaminate Phobos. Not uniformly, not across the whole globe, but at least in parts. And if for some reason I believe that this production would last through the history of the solar system, it could be a significantly deep layer of Deimos dust that is painting the surface of Phobos. So now I would like to move on. In addition to impacts, people always argued that exposure to solar wind can also move dust around on air objects. And this is just kind of a montage of things where people argued that dust lofting and dust transport might be at present, including the spokes of Saturn on the right, or the Surveyor TV cameras on the lunar surface, these hovering bright clouds after sunset. People argued that has to do with dust levitation. And certainly we already, Carly mentioned eras during not the landing, but towards the end of the mission. These close-up images showed very flat bottom craters filled with fine dust that, again, people argued that has to do with dust transport into those. And of course also the very large particles that Rosetta mission noticed at the comet. Gas drag seems to be not the right process, but maybe electrostatic lofting might be the one responsible to liberate them from the nucleus. The moon and Phobos and Deimos and all airless objects are exposed to solar wind plasma, electrons and ions, and of course ultraviolet radiation that makes this plasma environment quite complicated. On the day side, ultraviolet radiation would charge everything positive. On the night side, it's going to be negative, and there is a chance that you might loft particles. Before I do that, I have to remind you, of course, if you ever go to Phobos and Deimos, there is certainly any activity would generate a lot of dust. And this is very glorious, but what I would like to bring your attention to is these enormous rooster tails, big clouds. When you move around on a regolith in low gravity environment, you liberate certainly a lot of dust. And by the way, if you were to go back to the moon, that is a complicated environment to live in. And this is not so glorious, but nevertheless just as interesting.
Jack Schmidt having a few problems.
And of course, you might recall that the astronauts, the suits, everything got covered with dust that does not easily come off. So there will be issues regardless whether we go to Phobos and Deimos. And of course, we have these beautiful corrections of the Apollo astronaut drawings. Tells you that when the spacecraft was approaching local sunrise, these clouds appear to be following the lunar surface. The cloud that you see, like this is 6 minutes before local sunrise, is probably zodiacal dust. Light scattered by the dust between us and the sun. But as you approach the local sunrise, you see the brightness is appearing to spread along the lunar surface. That cannot be zodiacal dust. And then you can also see these rays of brightness that is typically argued for small particles lofted above the lunar surface. This is just to tell you that UV is changing in time. The charging environment is changing. When we argue that the solar energy production is not changing a whole lot from solar mean to solar max, the UV, the short wavelength part, is changing quite a bit. And that's the one that you care about ionizing the surface or generating photoelectrons from the surface. It's a quick calculation. I don't want to go through other than to tell you that the probability of a micron-sized particle to have a single electron is incredibly low. So it's actually really hard to lift particles, because if I make an estimate how big the electric field is, it's about a volt per meter or so, maybe 5 volts per meter. I multiply it with a single charge. It's really, really hard to lift off particles. But nevertheless, against our best judgment, we have done laboratory experiments, and we exposed particles in plasmas, flowing plasmas, and ultraviolet radiation, and we see them moving in the laboratory. And that's a heartache, because it's against my best judgment. Based on simple physics from the previous rides, there is no way you would move these particles around. On the left is GSC Mars simulants, because they are orange and they can be easily seen in a plasma chamber. And you see when they are exposed to 75 eV primary electrons, in due time they seem to be spreading in a plasma chamber. Other folks, like at University of Iowa, have done similar experiments when they exposed a dusty Christmas ornament to flowing electrons, and they noticed that small particles are jumping off intermittently from the surface. And that's a real puzzle. And then we try to show, and this is our latest experiment. These are actually sieved particles, 38 to 48 micron diameter particles in a crater that we filled with dust, and then we exposed it to UV radiation, and then we exposed it to flowing plasmas, and then we exposed to them combined. And what we noticed is these are images that are subtracted from one another, and the green are moving particles. We see them jumping off the crater, and that is incredible. These are huge particles in 1g gravity, that they are not fighting gravity alone, but they are also fighting cohesive forces. And on the left, you see their trajectories. They are popping out from the crater. So clearly, our ideas how particles get charged on surfaces is not quite right. And I am just offering something that's in the works, and that is the complicated structure of the very surface. When electrons and ions come in and they enter a void and they produce secondaries, it is possible that this particle on the top has a total charge that is very small, but the total charge is distributed very unevenly. So if these are photoelectrons, the top part will be positively charged because of the loss of photoelectrons, and the bottom part is photoelectrons that are coming from its neighboring particles landing, and they will charge the bottom negatively. And then if I have adjacent particles that are similarly charged, the forces between particles and particles can be surprisingly large. And that calculation I can do, and I can show you that it really beats gravity. So it's kind of we are back in our thinking to the fairy castle structures, and that is important in charging particles and possibly moving them around until the surface gets nice and homogeneous and flat. So just to show you again, particles in plasma and even in UV are popping out from the crater. So it is possible to move them around, certainly on the moon with much smaller gravity than on the ground, maybe Phobos and Deimos as well. So I'm on the last couple of slides. The access of solar wind to the surface certainly can be made more complicated by the presence of magnetic fields. This is a laboratory setup. There is a dipole. A kitchen magnet is hidden under the surface, and we have a plasma flow. And we try to simulate the conditions when people expect in SWIRS, the albedo markings at the moon. And this is kind of an interesting regime in plasma physics, because what I show you is distance from the surface, at least in our laboratory experiments, but this is also the case for the moon. And the red is what we call the gyro radius. Charged particles in magnetic field lines go around and around, more or less in circles, and those circles are tiny for electrons and very large for ions. This is what we call the electrons are magnetized. Their motion is dominated by magnetic forces, and the ions remain unmagnetized, so they just flow more or less unperturbed against the surface. And then you could measure what sort of electric fields you get, and it's going to be quite complicated. It's non-uniform, so the access of ions to the surface could be quite complicated depending on the magnetic field structure. And people have done simulations. This is actually from Andrew Poppy et al. This is a paper in Prince. When you look at Rainer gamma, and this white box on the top left is the simulation region, and you see these dark bands, or on the right, on the top right, you see the relative brightness. There is a bright spot, there's a dark lane, there's a bright lobe again, and then another bright lobe. And depending on the magnetic field structure, if you believe that the solar wind is responsible for darkening, if there's a lot of ions come in, they will darken where they land. Here it is. The top part, that was a better magnetic field model. You see something similar. And that I would refer back to Carly's talk, what exactly is happening when solar wind ions are hitting the surface. But maybe indeed these are the ones responsible to make bright and dark patches. And I'm towards the end of my time, but let me remind you that you don't even need magnetic fields. The electric field structure can be quite complicated just due to topography. And this is a crater. The sun is shining from the top, and this is what we call the photoelectric sheath, or the surface potential as a function of height. And of course, the gradient of the potential is the electric field. So this one is telling you that there is an upward pointing electric field. The surface charge density is positive, and the electric field is pointing away from the surface. If you wait a little, so the sun moves to 45 degrees, then regions that are not lit will receive electrons from other parts of the surface, and they will charge positively. So it is a complicated dance during the solar day of the electric field structure in a crater. You could land a spacecraft, and the spacecraft would make its little box here is a meter by meter spacecraft. And of course that will complicate because it will also emit and absorb photons and electrons and ions. And you could, I think this is my last slide or so. Imagine that on the top, the black line is a uniform distribution of dust. And then as you wait during the lunar day, you wait a little, those are the blue, you wait a little longer, those are the red, and the black indicates where the crater in this simulation is. Notice that there is a huge pile of dust at the bottom of a crater. And you say, oh, you shouldn't start uniformly, you should start with a different dust distribution. The black line on the top shows me that there's a huge pileup of dust on the left side of the crater. Soon enough, they will all end up at the bottom of the crater. So maybe this is related to piling up and giving you these dust ponds, the flat parts of nicely uniformly distributed fine dust at the bottom of the craters. This is just another image. And here I am at the last slide. If anything, perhaps this was good enough to convince you that the analysis and interpretation of remote sensing data could be complicated by dust mobilization, gardening, either due to meteoroid impacts or solar wind plasma or UV exposure that certainly is capable to moving dust around the surfaces. And of course, you could also deliver dust, at least in the case of Phobos and Deimos, from Deimos to Phobos. And as Carly pointed out, that the conclusions that we might arrive about space weathering and who is a player, who is more important than the other, could certainly depend on where you are in the solar system and even on where you are on the surface. Some regions are certainly more vulnerable than others. And with that, I am at the end of the presentation.
Okay, thank you very much, Mihai. That's really excellent presentation. Appreciate it. I'm going to start with you for questions, if you don't mind, because I think then we'll work back to Carly. So we have from UCF 445 the question: is the dust torus scattering large enough for it to be picked up by one of the current Mars orbiting spacecraft by observing scattering while the spacecraft is in the Mars shadow?
So we had an excellent opportunity. Siding Springs came by Mars last year, exactly, I think it was last year, when MAVEN arrived. And there was another spacecraft from India, Mars Orbiting Mission, MOM. And we tried to convince them to look at Phobos. They had a chance to see the burst of a dust cloud. But that observations was not done. But I think it would be quite possible. For example, certainly MAVEN noticed in the Mars atmosphere the metallic lines appearing, which is meteorites ablating in Mars atmosphere. I think Deimos was hidden, but Phobos was also exposed at the same time. But the total torus during siding springs, it was only enhanced for a short period of time. So the best of my knowledge, that measurement is yet to be done. But certainly an orbiting spacecraft, if you can arrange the geometry to be eclipsed by either Phobos or Deimos, that would be a very sensitive measurement to look at their dust clouds.
Okay, excellent. And Stephanie Eckert asked, would you expect a different level of accumulation of dust grains on different regions of the surfaces? For example, craters versus relatively flat areas?
Very much so. So the ejector particles are kind of tiny. So I imagine it could be like a two-step process, like considering Phobos and Deimos. The Deimos dust would arrive and eventually be moved around by solar wind interaction. So it is quite possible that most of the dust would in fact accumulate in craters on Phobos. Very much so.
Okay, and Richard Jarosek asked, where, based on studies of the moon and asteroids, do you expect a lower cutoff of the dust size distribution to be?
Oh. So I do know for simultaneously to LDEX measurements, the UV instruments also noticed big enhancements in brightness in sodium and potassium. So the size distribution extends to atoms and molecules. So of course, depending on how small you are and how much charge you carry, as far as like a cluster of particles, your lifetime could be very short. But I think it's a continuous distribution of sizes from solid matter, what we call dust, down to hundreds or thousands to hundreds to tens of atoms and molecules. So I don't think there is a lower cut.
So we lost your audio here. Yeah, we're up. Yeah, Ricky, we're not
Can you
here.
hear me?
Now we
There,
are.
okay.
Yeah, copy that. That's good.
Oh,
If you
okay,
could
so
repeat-
that long answer. Okay, so this was about, can you hear me?
Yes. Yes.
Okay, so the last question was about the size distribution of particles, which I try to argue that continuously extends all the way to atoms and molecules. So I don't think there is a sharp cutoff in sizes. Certainly there is a cutoff in the highest size, which we typically from lab experiments we argue that the largest particle that you generate in an impact is unlikely to be larger than the impactor itself.
Okay. So Richard Jarosek, for Phobos and Deimos, also it appears that smaller grains experience will end up with larger charge to mass ratios and experience greater electrostatic forces. Couldn't the smallest dust grains easily escape the moon's surfaces, increasing the lower cutoff of the regolith size distribution? So could you get rid of a lot of that and really change the overall size distribution?
That's a very interesting question, and I would like to tell you a little story, which is Otto Berg, when he retired. Otto Berg was the investigator of an Apollo experiment, LEAM, the Lunar Ejector and Meteorite Experiment. He gave me a folder of his correspondence with a guy named Horanyi, who was one of these guys who knew about spectra of asteroids. And then he said, how interesting. Could it be that the spectral classification of asteroids asteroids somehow relates to their size, because from small